Okay, we are at the top of the hour. Welcome back again, everybody. My name is Lori Krings. I will be your moderator again today. And we are at day 2 of Intro to Surface Water Treatment. So I'm glad you are back, and we're excited to have you back with us again today. So let's look at the plan for day 2 as we get settled and we have everybody logging in. Today's plan isn't really that much different from yesterday. Of note that I want you to have brought to your attention mostly is that we're going to be doing polls again today, and some of them might need, not all of them, but some of them might need time for calculation. So please know that we will be allowing for that today. So some of the polls might be open a little bit longer if you need time to crunch those numbers. And then we will, of course, be recording again today, and that will get sent to everybody later. We'll be taking a break. And if anybody has any questions for me to hold for the end of today, please do send them over through the chat or through the Q&A section of Zoom. That's fine. And also, if anybody has any accommodation needs, if not now, right, but to keep in mind that we are happy to work with people on those, just let us know for future trainings. If that would be something that you need, please do let us know. And then the biggest thing for your attention today is that if you do need a certificate of attendance, that at the end of today, I will be putting a SurveyMonkey link into the chat, and you will need to complete that survey within 24 hours. Okay, so just know that you need to be looking out for that at the end of today. And I'll be dropping the day 2 slides here into the chat in just a moment. Otherwise, we are going to start off with Daryl. Welcome back, Daryl. And we'll pick back up with where we were with Greg when Greg starts his part later in the day. Okay, so thanks, everybody. And hi, Daryl. Thanks for coming back.
All right. Thank you, Lori. Just an update. So I see this on the slide, the Georgia CECs. We found out today that Georgia approved 5.0 hours of water and management / safety continuing education credits, and that's from Georgia SOS. So certificates will show that. All right. So what have we been discussing? So yesterday we discussed water sources and quality. Greg covered coagulation, flocculation, sedimentation, was working on filtration, and he will finish that up after I am done talking about disinfection. All right, so we'll cover disinfection methods. I'll talk about compliance with surface water treatment rule regulations. Greg will talk about modifications of the treatment process. So why do we add chlorine, or why do we use UV or ozone? Because we need to kill the bugs, the pathogens that are in surface water. We need to kill those to provide safe drinking water to the public, protect public health. Disinfection is a primary, it's one of the primary treatment processes. It's pretty much covers all things. If a system's going to do any sort of treatment, disinfection will be part of that. Groundwater systems, the minimal thing that they would do would be disinfection, even if they don't do anything else. So surface water is required to do disinfection. So what does disinfection take care of? So there's 3 pathogens that we aim to kill or remove, inactivate from the water. Those are bacteria, virus, and protozoans. Now, how effective disinfection is, it's primarily 2 different things that affect how effective it is. And that's the residual concentration, or the amount of chlorine that we have, and also how long is that chlorine in contact with the water. So how much, it needs time to affect those different pathogens. And there's other factors that we'll see that come into play, but they're not nearly as important as the residual concentration or the contact time. Now, we mentioned cryptosporidium because that's something that chlorine is not good at disinfecting. So we have other methods that we can use throughout the treatment process to remove the chlorine. All right, so the primary disinfectants, I had mentioned we have chlorine. So that's effective at killing the bacteria and activating viruses and protozoa. As long as we give it enough, a high enough concentration, and we give it enough time to do that. And one of the important things about chlorine is it has a lasting residual. So that means that after we apply it for a given amount of time, it's going to continue to be able to do work on those bugs. But as we had mentioned, it's not effective against cryptosporidium. The other side of this is that throughout the system and into the distribution system, it can produce disinfection byproducts, which are something that's regulated by the Safe Drinking Water Act, and we want to minimize the production of those. The second of these is ozone, and it's created by passing oxygen through an electrical discharge. So it converts the O2 or the oxygen into ozone, O3. It's very powerful. It works well, and it kills all of our 3 pathogens. One of the issues with ozone is that it doesn't last a long time. It has a residual, but it's a short residual, and it can also create disinfection byproducts in the form of bromate if the water that it's treating contains bromide. So bromate is another disinfection byproduct that we try to avoid creating. So, and then the third is UV light. It's a light, UV light's at a wavelength of 254 nanometers. That's effective at killing pathogens. But then it not only has it got less less residual, it has no residual, excuse me. The water in for UV light must be very clean so that the light can penetrate the entire thing. And as we see in these, there's no perfect disinfectant. We can use different ones for different purposes. Each has their pros and cons, and we'll see more about this later. So what's the health impact of chlorine disinfection? So this chart shows death rates from typhoid fever in the United States over a 60-year period. And as you can see in the early 1900s, it was pretty prevalent. There were thousands of deaths that occurred, but nobody really understood why. What was causing the deaths. And then in the 1670s, they first were able to observe microbes underneath a microscope. So they started to see them, but it's hard to link them up, I guess I would think at that point. In 1854, John Snow discovered at the Broad Street pump the cholera outbreak in London, and was able to associate cholera as a waterborne disease. It's a really interesting story. So if you're interested in history and in part how history can, the history of things like water treatment, I would look up the Broad Street pump cholera outbreak. And then in the 1860s, Louis Pasteur was able to, he developed a theory about microbes causing infection. So just furthered the ideas that these pathogens are out, these little bugs are out there, and that they could be causing issues. And then in 1908 in New Jersey, we had the first system that in the U.S. that chlorinated drinking water. So that's a huge development, and that kind of correlates with, if we look in 1908, we had approximately 24 deaths per 100,000 people from typhoid. And then we can see a decline throughout time. And a lot of that has to do with, improvements in all sorts of public health things. But, chlorine, the application of chlorine is definitely crucial. It became more common through time, and those the death rates reduced significantly. So down to the point where it's less than a death per 100,000. So, all right. So, Greg had mentioned yesterday that I had spent time as a state regulator, and this was one of this chlorine curve, and as I like to call it, breakpoint chlorination, is one of the things that the most important concepts. You don't need to memorize the chart necessarily. It's just the idea behind this. So as we go through this, we note that as we add chlorine across the bottom here, the chlorine residual, it has an effect on the chlorine residual. So we start off, and the initial thing is that these reducing compounds, they affect, as we add chlorine initially, we're not getting any residual at all, because they're destroyed by these reducing compounds. Reducing compounds are typically inorganic substances like dissolved iron, manganese, and hydrogen sulfide, as well as organic materials such as ammonia and other nitrogenous compounds. So that our initial chlorine application results in no chlorine residual because it's getting destroyed. And then, we keep adding chlorine. And as we add chlorine, that chlorine is, it produces chloramines. And chloramines are the things in drinking water that give that taste and odor. So I said that this was an important concept that I wanted, I tried to impress upon, the regulated community back when I was working for the state. And it's because it's counterintuitive. The idea is that the more you apply, you'll get to a point where it stops increasing. And so that's called breakpoint chlorination. So, initially we form chloroorganics and chloramines, and then the chlorine starts to destroy that. So we're reducing that. Our residual actually goes down initially, but we're getting rid of those things. And we get to the point where we get to this break point. And at that point, the chlorines or chloramines and chloroorganics are destroyed, and we can start to actually produce additional, I'm a little behind in my slides, free residual. So what we apply starts to we actually see that. So this concept that you're gonna, it's gonna get worse. Your residents will complain, you'll get calls, it's gonna get worse, it'll start to get better, and then you'll get to the point where as you apply, it's, what you apply is going to result in residual. So it's a hard concept, but it's an important one, I think, for, if you're adding chlorine. So that area that between, we have an area here of combined chlorine. The area above is free chlorine. So this will be important as we talk about this a little bit later. So here we go. We extend our chart out. This here is our free residual. So that's chlorine that's available to work against those pathogens, those bugs. And then we've got an area of combined residual. So if you were to go out and do testing in your, say your distribution system, and you do your test kit for free residual, you get a number. You do a test for combined residual, you get a number for that. Well, your total residual is going to be the combination of those two. So if we look at this, the concept is that the dose is equal to the demand plus the residual. So a dose of 1.5 milligrams per liter of chlorine is added to water, resulting in a measured free residual of 1 part per million and a total residual of 1.3. What is the demand from reducing compounds? So we had mentioned before that we weren't seeing any residual initially due to those reducing compounds. So we have 1 part per million or milligram per liter of free residual. We have 1.3 of total. So, I mean, that would tell me that our combined is 0.3, the difference between our total and our free. But if we applied 1.5, what would our demand from the reducing compounds be? Well, we take our dose, which was 1.5. We subtract out our total residual of 1.3. And that tells us that the demand from the reducing compounds is 0.2 parts per million. So getting that all out here, we've got 1.5 as a dose, we have 1 of free, we have 0.3 of combined, and we have 0.2 of used up by the reducing compound. All right, I guess it's time for the first poll. So poll number 1, drinking water with a demand of 0.4 parts per million has a total chlorine residual of 1.7 parts per million. What was the chlorine dose? Okay, we got some math to do here, so we'll give you guys a little bit, maybe a little extra time just to make sure everybody gets a chance to get through that. Let's see. Getting about, guessing about half of the.
Half, yeah.
All right, there.
80% have answered.
All right. You said, well, I mean, I know it can take a little bit more to do math problems, so we give a little bit more time for this. Make sure that everybody gets a chance.
Got 72 of 85 have.
Okay, well, let's see if there's another response. All right. Okay. I haven't seen an answer come in a little bit. Yes, Lori, if you would end the poll. All right, so the responses we have are 2.1 was 80%, 1.3 at 12%, 1.4 at 7%, and then 1% for D 5.7. So let's go through this. So we have a total chlorine residual, free and combined, of 1.7, and we have a reducing compound demand of 0.4. So therefore, our dose would need to be the combination of the reducing compound demand and the total chlorine residual, free and combined. And the answer is 2.1. Which is answer C. So majority of the people agree, I guess. Okay, so now we'll move on and we're going to talk about the different types of chlorination. Chlorine, there's 3 different ways that it's typically added to water systems. It could be as a gas, as a liquid, or as a solid. we'll first start talking about gas chlorine feed rates. So as you can see, the canister, it's a liquid, and there's a gas at the top. So we take that gas off, and that's what gets put into, injected into the water stream. So from this, if we want to know what our feed rate needs to be in pounds per day, we take our 1,000,000 gallons per day, or our flow, we multiply it by our dose and by the weight of water, 8.34 pounds per gallon, and that'll give us the number of pounds per day. So this is a rotometer, and the rotometer will show us in units of pounds per day what our feed rate is. It goes up to 40 pounds per day as a max. I'm going to note that pounds per day is a rate of feed. Okay. So using that formula where we have pounds per day equals flow, or 1,000,000 gallons per day, times our dose of milligrams per liter times the weight of water. What is the feed rate setting for chlorine gas in pounds per day if the plant flow is 1.2 million gallons a day and the dosage is 1.5 parts per million? So we're going to plug those numbers in. So we'll put our 1.2 million gallons per day in for flow. We'll put in 1.5 parts per million, or milligrams per liter, for our dosage in the formula. And our constant of 8.34 pounds per gallon, it doesn't change. So we have 1.2 milligrams or million gallons per day times 1.5 parts per million times 8.34 pounds per gallon gives us 15 pounds per day. So for that flow and that desired dosage, that's how many pounds of chlorine gas. Now, it's in a gas, but it has weight, and so you would measure, like I said, you can dose it, and you'd also measure how much. That would be 15 pounds. The tank would be 15 pounds lighter in a day at that rate. So the pounds formula is an important formula in all sorts of dosing for water treatment. So that formula, pounds per day equals flow times dose times the 8.434 pounds per gallon. 1,000,000 gallons, how many million gallons total in flow? Parts per million, how many millionth parts in each 1,000,000 gallon? And then the weight of water. Weight of substances in water is considered a portion of the total weight of the water. All right, so we had 1.2 times 1.5 times 8.34. It gave us 15 pounds in a day. From that, we can figure out the weight of water. We'll take we convert our 1.2 mgd into actual gallons. And that tells us that our water itself weighs 10,008,000 pounds. And if we take our parts of chlorine and divide it by 1,000,000 parts of water, and we multiply that by the weight of our water, it gives us 15 pounds, the weight of chlorine. So we can work these problems in different directions. As it says, the pounds formula can be arranged to solve for dose. So we take our pounds formula. We want to find that dose. So we're going to divide both sides, or both sides of this equation by 1,000,000 gallons per day, our flow, and by 8.34 pounds. So pounds per day stays on over here. We put these underneath both sides, and then we can cancel these out because they're the same. And so what it does is it gives us the dose is equal to the pounds per day divided by the flow times the weight of water. So a lot of operators are learning different ways to do things. And in this case, we can use the pi formula. I've also called it, heard it called the picnic formula, to do this. And so on the top of this, we have the feed rate. On the bottom, we have the flow, the dose, and the weight of water. To solve this, the information on the top is going to be equal to the multiplication of the 3 on the bottom. So 1 million gallons a day times the dose times the weight equals pounds per day. It's pretty much the same. Some people, this is an easier way for them to understand. So let's do we'll do an example. We'll calculate the gas chlorine feed rate for a plant with a flow of 0.6 mgd and a dose of 0.9 or 0.9 milligrams per liter, 0.9 parts per million. So we can put these in here, so we see where they go. We throw the numbers in, multiply it out, and it gives us a feed rate of 4.5 pounds per day. So in this, the solution is on the top, or what we're looking to get is on the top, and we've got these 3 factors that we multiply. It's pretty much the same as our pounds formula. So we can solve for things that are on the bottom. So in this example, we're going to want to know what the dose is. So what we're going to do is we're going to use the same. We're going to work this problem as if we didn't know what the dose is, but we knew the pounds of the 4.5 pounds per day, and we know the flow. So then our dose, and we had figured this out before, is equal to the feed divided by the flow times the weight of the water. So that gives you the bottom. So in this case, when using this pi formula, you can take and solve for any of these 3 by putting the top above the fraction, on the top of the fraction, and then the other 2 factors multiplied on the bottom. So in this case, it works out to what we expected, a dose of 0.9 parts per million. And we had manipulated our pounds equation to come up with that dose equation previously. All right, we're already on to poll number 2. Let's see. So for poll number 2, an operator checks the settings of a treatment plant and notes that the gas chlorine feed rate is set at 30 pounds per day and that the plant flow is 2.1 million gallons a day. What's the dose of chlorine in parts per million or milligrams per liter that is being administered to this water source? We'll give some time. We've got some responses coming in. I think one of the things is to make sure that you're using the proper formula, because it's asking for what the dose is. So we'd want to use the formula that the answer is the dose. We're up, well, it looks like just under half the responses in. Try and make sure we give everybody that wants a chance to answer the poll, a chance to do that before we reveal the results. All right. Yeah. Give it a few. It's been a little bit since I've seen a response come
Yeah,
in.
looks like just under 3/4 have answered so
there-
far.
I understand these, sometimes working these math problems, making sure that we have the right formulas can take a little bit of time, so. I'm sure there's people out there that it's very easy for, and there's
Yeah.
others that we need to make sure to give the time. All right. Looks like the responses have slowed down.
Yeah. I think so.
Okay. All right, Lori, can you end the poll, please? Oh, we got a note poll. Okay, we have, if you ever are in a situation where you can't see the poll, feel free to put your response in the chat. That happens on occasion. So let's see. Responses that we got, 73% said A, 17% said B, 5% C, and 3% D. So let's go through and let's see what the response should be. So we're using our dose example of the pounds equation. So the dose is equals pounds per day over the flow in million gallons a day times the weight of water. So we know that our flow is 2.1 million gallons a day. We know that we have 30 pounds per day as our feed rate. So our dose is going to be equal to our pounds per day feed divided by the million gallons per day of water of 2.1 and by 8.34 pounds per gallon. So that gives us 1.71 milligrams per liter. And that corresponds with answer A. All right. So we covered gas chlorine. So let's go on to calcium hypochlorite. So this would be considered the solid or the powder version of chlorine. It's also called high test hypochlorite or HDH. Now with this, we need to take into consideration that it's not like gas chlorine. Gas chlorine is 100% available chlorine. And both calcium hypochlorite and our liquid chlorine are going to be at concentrations less than 100%. So as we see, we're going to have to take that into account by dividing it by the percent strength that we're given. So the top part of our equation is going to give us the pure chlorine, and then dividing by that percent strength is going to take into account that it's not 100% available. We go back, just make sure that we note that calcium hypochlorite or HDH can be in several different forms: tablets, pellets, powder. I've heard it referred to as pucks. So just know that it comes in a lot of different forms. It's also, one of the more common places it's used in is the installation or chlorination of new water main. So let's see, how many pounds of 65% strength HDH are required to disinfect 0.6 million gallons of water with a total residual of 1.5 parts per million. There's a note here. The top part of the equation indicates that we would need 7.5 pounds of 100% strength gas. So let's see, let's work this. So if you use the calcium hypochlorite formula, it's just the pounds formula with the percentage strength below it. We multiply those out, 0.6 million gallons times 1.5 parts per million times the weight of water divided by 0.65. That gives us 7.506 pounds. We divide that by the strength, and it gives us 11.5. So for gas, we'd only need 7.5 pounds. And that's indicated here. This is basically the formula. The top of this equation is the formula for gas chlorine. But because it's only 65% strength, we need more of it. So we need 11.5 pounds of HTH. All right. So that's about all we're going to cover on HTH. We start to look at liquid chlorine. We have to talk about specific gravity. So specific gravity is the ratio of the weight of a substance to the weight of water. So how does it compare? How does the weight of that substance compare to the weight of water? And we're talking about liquids for both cases. Water is a liquid, and we're going to compare, when we talk about specific gravity, we also are talking about liquids. So if water weighs 8.34 pounds per gallon, it has a specific gravity of 1.0. So compared to itself, it weighs 8.34 pounds per gallon, and our standard is 8.34 pounds per gallon. This is it. For specific gravity, we're comparing it to water. So sodium hypochlorite, or liquid chlorine, weighs more than water does. So we're talking about a common strength of liquid chlorine is 12.5%. In that case, it has a specific gravity of 1.2. So that means that it is heavier. A gallon of sodium hypochlorite is going to be heavier than a gallon of water. So it actually, if we go through the calculations, if its specific gravity is 1.2 and the weight of water is 8.34, that means that liquid chlorine is about at 12.5% is about 10 pounds per gallon. So if you're hauling that around and you're wondering why you're breaking your back, it's because it's even heavier than water. So when we're going to calculate feed rates for liquid chlorine and sodium hypochlorite, we added in the percent strength when we were looking at HTH. Now we have to put in the weight per gallon. So that'll help to get us an accurate amount of, or pounds per day. So on the top, the equation is the same as what it was for pure chlorine. In the bottom, we're going to take into the percent strength as we did with HTH, and then we're going to need to take into consideration the weight per gallon of the liquid chlorine. So, a common concentration for liquid chlorine is 12.5%. For our percent strength, we're going to make that into a decimal form, divide that percentage by 100, and we'll have 0.125 for our calculation. So in this case, our gallons per day becomes million gallons a day times the dose times the weight of water divided by the percent strength times the specific gravity times the 8.34 pounds per gallon. All right. The specific gravity, as we said before, times the weight of water gives you the weight per gallon of the liquid chlorine. All right, so let's look at an example. What is the feed rate for 12.5% sodium hypochlorite with a specific gravity of 1.2 when the plant flow is 0.5 million gallons a day, 500,000 gallons a day, and the dosage is 0.9 parts per million? So we're going to use the formula. We're going to plug in those values for flow, dosage, specific gravity, and solution strength. So there's our formula, modified for the fact that we don't have full strength and we're using liquid chlorine. So throwing those numbers in, the 500,000 gallons a day, because 500,000 gallons a day, our concentration and our percent strength, specific gravity, these numbers all come in here. from what we were given. We go through that calculation and we multiply across the top, we divide by the numbers on the bottom, we get 3 gallons per day. So this is an example of, of a chemical feed pump. It's an LMI pump. These are considered positive displacement pumps. So you'll note that these pumps have the speed, so that tells you how quickly it works, and then the stroke, that's how much goes into each time the pump pumps, how much it pumps, and this is how quickly it pumps. And those things can be adjusted. There is a maximum, this is the maximum number of gallons per hour, 0.58 gallons per hour that this pump is capable of pumping. And that's when both the speed and the stroke are set at 100%. So, we have need to know how much do we expect a pump to pump. So if we go through, we can calculate the actual output is going to be, we're going to take into consideration our maximum output, and then we're going to multiply that by the setting that we've set for the percent of the stroke and the percent of the speed. So in our example, it's got a max of 0.58 gallons per hour. If the stroke and the speed are set at 70%, what's it actually going to produce? So the actual output is that max multiplied by the percent stroke and speed. These are flip-flopped, but you get the same result in this case. And so that's the actual output of a pump. This pump at 70% stroke and 70% speed is 0.284 gallons per hour. So it's a little less than half, or a little less than half of what the pump's capacity is. So that's a good setting. If you can get by with a setting that gives you about half of the pump's capacity, that means that you've got room to either increase or decrease that pump's output. So this would be probably a good pump. If we need that 0.284 gallons per hour, this is probably a good pump for our application. And if we want to find out how much it can pump in a day, that might be important for you if you've got a day tank that you're pumping out of and you want to be able to, pump the entire day. How big of a tank do you need in order to be able to pump for an entire day? And that equals out, if we multiply that by the 24 hours in a day, we get 6.82 gallons per day. So this calculation, we can compare that output to, what we need from from our previous calculation where we came up with 3 gallons per day. So this would definitely pump at least what we needed. So when we were talking, there, the important things are the concentrations. We've covered a lot of the information about chlorine concentrations. But now we're going to talk about that contact time. And so, there's a theoretical detention time, and the amount of time that chlorine will be in contact with the water. And that assumes that there's no short circuiting. So the water's not getting around, getting contact with that. So, it's simply the time is equal to the volume that we have, how much water, and then what our flow is. But that doesn't happen in most cases. That might be the case if you've got, you're putting into a pipe. But if you're putting it into a tank, quite often they'll have to have baffles in those tanks in order to make sure that the water comes in contact, or that the chlorine comes in contact with all the water, and we don't have short circuiting. So our time is changed. We're going to take our volume in gallons, and we're going to apply a baffling factor to that, and then we'll divide that by the flow. So this is clear wells are the areas at the end of treatment plants where we're trying to get that contact. We're trying to introduce that chlorine into the, to the water and make sure that it gets to all of it. So it has a chance to work on all of those pathogens. So as you can see, this flow visualization here on the right, the areas in red and orange are areas where there's higher velocity flow. The areas in blue and green are lower velocities. So in theory, we want to get rid of the blues and get rid of the reds and have everything be kind of yellow or green. And that makes, under those circumstances, we don't have water that sits there for a long time, or we don't have water that just zips through our system. So baffling factors are an indication of how good the baffling is and how well our water gets mixed. So if you've got a situation shown here where pipe comes in and it's, water can just go straight to the other pipe, it's not very effective. It's better than if they were both, very short pipes and one came in and went straight over, but it's not the best situation because our contact time is really limited. Some of the water could just go from one to the other and not actually get in contact with chlorine, have time to contact the chlorine. So this is an example of either unbaffled or poor baffling conditions. The figure on the bottom is, that's better. We're giving it time and we're forcing it to go around. It spends more time instead of going straight across. It has to go through these series of loops here. So that's a better. So the baffling factors increase. A perfect plug flow in a pipe maybe or something like that, we wouldn't worry about it. We would, baffling factor would be 1. So let's do a little example here. What's the disinfection contact time for a tank that has a volume of 75,000 gallons and a baffling factor of 0.5 if the flow is 500 gallons per minute? So we have 500 gallons a minute. Our clear well, the total volume of this is 75,000 gallons. And our solution, we're going to take our 75,000 gallons, the total for the tank. We're going to multiply that by the baffling factor. So that's going to reduce the amount of actual time that we're seeing because it's a factor of 0.5 compared to, say, a straight pipe of 1. And we're going to divide that by the flow. So it's the volume divided by the flow, and we're going to multiply by that baffling factor. So that gives us 75 minutes. So if this was a straight pipe and we'd see twice that, we'd see 150 minutes worth of contact time in a straight pipe under the same set circumstances. So the next topic, we're going to cover CT, comparing the contact time values and the log inactivation requirements. So the surface water treatment rule requires that we have, they call them log inactivations. Giardia has they want 99.9% of it to be inactivated. And for viruses, it's 99.99%. So they consider this a 3 log that's going, 0. If this weren't percentage, if it was actually, it's 1 out of 1,000 or 0.001. And this is 1 out of 10,000. So that's where the 3 and the 4, it's another level of from 3 to 4 that they're requiring. And Giardia only requires a 3 log removal because the pathogen, the bugs are larger, and so they're easier to remove from processes like filtration. And on top of that, viruses are a little more resistant to disinfection, as we've indicated, and they're a little more harder to filtrate out. So the combination of the filtration, so Greg had talked a little bit, and he'll talk again about filtration, and then the disinfection that we're talking about today must achieve a minimum 3 log removal for Giardia lamblia cysts and a 4 log for the removal or inactivation of viruses. So we can combine both our treatment that we do through filtration, and we can with our CT and our disinfection to meet these requirements. So we can do a lot of things to aid in the process. I talked yesterday about protecting source. We're talking about filtration. There's things that we can do that make sure that we're getting the most out of everything that we do. So if we have a source protection where we don't allow these pathogens to enter the water, then there's fewer of them that we have to take out. So the other thing we need to consider is the formation of disinfection byproducts. So chlorination, at high levels is not necessarily the answer to all of our problems, because high levels of chlorination are going to increase our disinfection byproducts. And then every state or regulatory agency has their own specific requirements. So we have to take that into consideration. And then our plant design will result in removal credits. And those removal credits are determined in combination with the Safe Drinking Water Act by our regulatory agencies, whether that's a state or for the tribes that are regulated by EPA. So this table, it is a table for 4 log inactivation of viruses with chlorine. You'll note that, so this is the amount of contact time that we're going to be required to have. And it's affected by pH, because these lower pHs require less time than a high pH of 10. It's also affected by temperature, because chlorine is more effective at higher temperatures. So therefore, at the same pH, we'd need less contact time with warmer water than we would with cooler water. So we match the daily minimum temperature with the daily maximum pH. And as I said, disinfection is more effective at higher temperatures. So in this example, you measure your pH and your temperature. So if you had a temperature of 16 degrees, you would choose the 15 temperature, because that's less, it's going to give you more conservative results. You're also going to choose, if you have a pH of 7.5, it's within this range. So we've got our pH, we're on this range. And let's get this caught up, and we've got our temperature is here. So that tells us from our table that we need to attain a CT value of 4 or greater in order to satisfy our requirements. All right, so let's look at a log 4 virus inactivation problem. So you got a small groundwater system, and they maintain a minimum free chlorine residual of 0.8 parts per million. So that's going to be located at where it's leaving their well house or their treatment plant. And then contact time is provided in a 3,500 gallon pneumatic storage tank with a baffling factor of 0.3. So it's not, you don't expect a pneumatic storage tank to have great baffling factor. So that's probably about right. Determine if the system is attaining sufficient CT for 4 log virus inactivation when the water temperature is 16 degrees. So we'll be looking here, and the pH is 7.5. So we're going to need a 4 for a CT. So what is our actual contact time? Our 3,500 gallons times our baffling factor divided by our maximum flow. That gives us 5.25 minutes. So we need to have our chlorine in contact with that water for 5.25 minutes. So what are we actually attaining? So if we have 0.8 milligrams per liter or parts per million, and we multiply that by our 5.25 minutes that the water is going to be in contact with that chlorine, we get a 4.2 milligram minute per liter, which when we compare that to the number from our table, which is 4, we are greater than 4. So that means that we met our requirements for our CT for 4-log virus removal. So I think I mentioned earlier that pH can have an effect on our chlorine. That was one of those other factors. And from this chart, you can see that you know, what we have, whether it's hypochlorous acid or the hypochlorite ion, it's determined by our pH has a major effect on that. So what we prefer is that we have this hypochlorous acid. It's more effective. It's better at getting to our pathogens. So this is what we want. So if we have a pH around 7, we have 80% of it is, let's pull these forward. So that means 80% of what we have is going to be the hypochlorous acid, and only 20% is going to be the hypochlorite ion. So this shows you as we get closer to a pH of 10, we've got virtually no hypochlorous. The stuff that works good against our pathogens is pretty much non-existent. So that's why pH has a major effect on it, on our on chlorine application. So this is a Giardia inactivation table. So we've got, as we had said, Giardia is typically we have a 3-log removal. So this goes up to 3 logs. And this table is going to help us because we're going to get some log removal from our treatment, and that'll be determined by the state, as I had said previously. But we'll have to use chlorine to make up the difference. So in this, we measure the free chlorine residual at the end of the disinfection process. So when we're done disinfecting, we measure that. And we also, at that same point, we measure the temperature and the pH, same location. So we choose the table that fits, that best matches our temperature. And we use the next lowest for temperatures in between. So let's go on to an example here. So this is kind of working backwards. So if we have a chlorine concentration of 1.2, and we're trying to get a 3-log inactivation with a pH of 7, we're going to need 76. We're going to need 76, a contact time of 76 minutes to achieve that 3-log removal. All right. So if we go into, now we'll go into another problem mode here, just to show how we can calculate this. We have a flow of 800 gallons per minute entering our clear well. It's chlorinated to have a free residual of 1.2 parts per million, and the clear well is 75,000 gallons in capacity. It's got a baffling factor that's pretty good of 0.7. The minimum water temperature is 15 degrees Celsius, and the maximum pH is 7.0. So remember, those are things that we need. We need all these things from our table. The minimum free chlorine residual is 1.2. Determine if the system has sufficient contact time and residual to achieve 3-log inactivation for Giardia. All right. So our contact time, we've got 75,000 gallons. That's the capacity of our clear well. Under the volume, we have a baffling factor of 0.7, and we have a flow of 800 gallons per minute. So that tells us that our contact time for our water through this clear well is 65.6 minutes. Now our CT is going to be our concentration of our free residual multiplied by the time that we came up with here, and that gives us 78.7 milligram minutes per liter. So we can look then at the table. So we've selected a table for 15 degrees Celsius. Our Our pH, we said, was a max of 7.0. We're trying to get 3 log removal. So our chlorine concentration is 1.2. So that tells us we need to get to 76. All right, so required CT is 76 milligram minutes per liter. Our calculated, we did on the previous slide, was 78.7. So that also exceeds our minimum required CT. So therefore, we're still in compliance. They're not going to send us any nasty grams. So if we want to actually go into the log inactivation and see what the actual, we know we met it, but how does that compare to the 3? So our log inactivation is 3 times the CT achieved, and then we divide it by the CT required. So in this case, we achieved 78.7. We were required to get 76. We know that top number is bigger than the bottom number. So it's the end result, the log removal is going to be above 3, and it has actually 3.1. So we achieved that log removal without adding chlorine. So let's look at another example. Removal and inactivation. So we're going to combine these, and we're going to conventional water treatment that has a removal credit of 2.5 logs. A minimum additional 2.5 log is required of inactivation to achieve our 3/8. So we're getting from our treatment process, short of chlorination, without chlorination, we're getting 2.5 logs. We need another half to get to our 3. So what CT do we need to achieve with disinfection if the temperature is 15 degrees Celsius, the pH is 7, and the residual is 1.2? So there we are. So our pH is 7. This is the right table because we're at 15 degrees Celsius. We have a residual of 1.2. Follow that across, that tells us 13. A minimum CT value of 13 needs to be achieved through disinfection. The rest of us already, the 2.5 that we got before of our log inactivation was already, we already got that from our treatment short of chlorination. And that 2.5 would be determined by, your state drinking water agency. And when they do that, they look at all the treatment processes to determine that number. All right. So some plants, to increase their log removal, they'll actually add chlorine at different points in the treatment. So in this case, we've got chlorine injected here on the intake line prior to coagulation. We're injecting chlorine after filtration so that we get our CT time in the clear well. And we would monitor. We'd monitor here because this is after and before we add in chlorine, and we modify after the clear well as well. So there's 2 points then. We have 2 application points and we have 2 monitoring points for our inactivation. I've seen systems that actually add chlorine at the beginning, like outside, just inside their intake for things like zebra mussels and stuff like that. So sometimes they're doing it to get the log inactivation, and sometimes they're doing it for other issues. So the other thing to keep in mind is that what if you're adding it, does it affect your processes throughout? Because the whole treatment chain can be affected by adding chlorine. And the other thing is, the more often we add chlorine, especially early in the process, we definitely have a higher risk of forming disinfection byproducts. We have more time for that chlorine to form these disinfection byproducts. And so we've been talking about them. What are they? So there's 2 sets. There's the total trihalomethanes, and those are these chloroform, these big bromoform, and all these big words. but we look at them as a total, and they're a volatile organic compounds that are known to cause or pose a concern for cancer. So they set a limit for the total of these four of 0.8 parts per million. And it's based off a locational running annual average. So you may have two locations out in your distribution system, and each one is independent. They look at that, the average is based off of an annual. So if you collected first, second, third, fourth quarter of 2024, at the end of the fourth quarter, they average those and compare that number. Well, then in the first quarter of 2025, you get another sample. Your oldest one goes off the books, and now we're making that average in comparison to the most four recent. So it's a location and locational average because it's by each of the individual locations, but it's also a running annual average because new ones come on, old ones fall off. It's always the most recent four. Hope that makes sense. And it's the same type of thing with the haloacetic acids. There are weak acids that can also pose, cancer risk. And so the MCL for those is 0.6 parts per million. And it's the same type of running annual average. These samples are collected simultaneously. THMs and HAs are collected at the same time in the same location. And they can both, react. Chlorine will react with the natural organic matter, and it causes the formation of these. And as we said, throughout time, they can, the more time the chlorine's in contact, it's a good thing for killing bugs, but it's also a bad thing for the potential of forming these disinfection byproducts. So now we're on to poll number 3. So poll number 3 says a 30,000 gallon clear well with a baffling factor of 0.7 has a flow of 500 gallons per minute passing through it. A chlorine dosage of 2 parts per million is required to achieve a free residual of 1.7 parts per million. What CT value is being achieved in this clear well? All right, we'll give some time. All right. Let's see, we're getting some answers in. And these math problems take a little more time than some of the other poll questions.
Well, more than half of folks have gotten their answers in.
Yeah. I don't know how much people can see behind this, whether it's worth going back to the slide showing the formula or not. I should have gone here. Oh, I'm just gonna go back.
There you
I
go.
was trying to find a slide that would help out with that. supposed to be. Sure. All right, we are. Those of you who've got your answer quickly, can kick back. Gonna give you a little more time.
70% of folks have answered now.
All right. All right. Oh, there are a couple coming in. All right. I think so we're not getting you guys out too late. I think we're gonna have to move on. Lori, you can end the poll, please. So let's see. We have at 52%, we have D 71.4. At let's see, 27%, we have C 84.5. At 18%, we have B 102.1, and at 3% we have A 120.3. Pretty wide range of responses. So let's see what CT value is actually being achieved in the clear well. So we take we can find our time by multiplying our 30,000 gallons by our baffling factor. You divide by our flow, and it gives us 42 minutes. We take our 42 minutes to determine our we use that to get our CT. We multiply by our free residual of 1.7. That gives us 71.4 milligram minutes per liter. And just a reminder, we need to use that free residual measured at the end of the disinfection process, just after the clear well. And that's important because if we took that number earlier on, it might show, it would likely be higher. And so, this is the worst case scenario. We're getting at least this. Hopefully we're getting more. All right. So I had mentioned there were three main ways that we can do disinfection. UV is the second of the three. So that's when we take, we've got UV light with a wavelength of 254 nanometers, and it messes with the genetics of our pathogens. So it's fast and lethal to pathogens. It's quick. It happens. It's very efficient. Unfortunately, there's not a residual associated, and disinfection only takes place in this unit. And these lamps that are inside also have, one of the downsides is that they have a limited lifespan. With these, we also have to have very clean water because the UV light needs to be able to get to all of the water. If we've got dirty water, we have things that will block it. In the United States, only about 10% of surface water treatment plants use UV. So, and they're typically going to be the larger systems. And keep in mind that in order for this to work, all the water would have to go through this tube or a series of these tubes. So it can be kind of expensive. And notice there's this UV disinfection guidance manual. These EPA guidance manuals are great. I'm a huge proponent of that. So if you're interested in UV disinfection, definitely go to that and check that out. And any of these that we have up here they're great sources of information if they pertain to you. So UV disinfection, the major thing I like to get off this is just the time that it takes, like time in seconds for 100% lethal dose. E. coli, it's 0.36 seconds. So that's pretty quick. That's going to happen, instantaneously. So, and it gets up to, crypto and giardia a little less than 10 seconds. So that means that UV light has to be in contact with the water, for at least 10 seconds in order to get that removal. And these are all, it's actually, this table shows it at this 30,000 microwatt seconds per square centimeter. And most dosages are actually a little higher. So these numbers would probably be in an actual use in a plant would actually be potentially lower than that because we're using a higher dosage. So as I said, the takeaway from this is that it's typically pretty quick. So what is using UV, because as I said before, we're going to use chlorine to have that chlorine residual that goes out in our distribution system regardless. So UV gives us some additional range of disinfection because chlorine will take care of most of these things. It does a pretty good job, but UV is going to get this crypto. So it's got an additional area that it can take care of. Crypto it's in a cis form where the organism's encased in a protective shell, and that's why the chlorine can't quite get into it. But UV destroys that shell and makes it allows it to deactivate that organism that's inside the shell. And the use of UV can allow us to put in less chlorine. So that can have UV is very beneficial in systems that have issues with disinfection byproducts. I mean, I remember a system that went to UV because they had a lot of issues with disinfection byproducts. So let's see. So where would you put this in the treatment train? It's always important. We have, a lot of plants were designed a certain way, and maybe you don't have room for it in your plant. So that's an important thing. It typically goes before, after filtration and before the clear well, and before we add chlorine back into the system. So as you said, microorganisms, if there's turbidity over 5 NTUs, that can affect the efficiency of UV disinfection. So right there is where we would put it after the filters, before the clear well, and before chlorination, or at least final chlorination. So what are some of the maximum levels of these contaminants that will still, what's the most we can have in the water and still have UV disinfection? So for turbidity, suspended solids, we've got 5 NTUs, and that's because they can block the UV lights from getting to those microbes. Iron and manganese can follow up the quartz sleeve that surrounds the UV lamp, and so that doesn't allow the light to penetrate through the water and get to it. And then pH, that can also, it could allow low pHs. It could allow to some scaling. We talked about that hardness and stuff. It could allow scaling on the inside of the tube, and once again, not allow the water to get through. So now we're on to our third type of disinfectant, and that's ozone. Once again, ozone's a powerful oxidizer. It's can be a very good disinfectant. It kills most all of the pathogenic organisms, including crypto, because it oxidizes the outside. Chlorine is an oxidizer as well, but ozone's a little more powerful one. One of the downsides to ozone is that it's very energy intensive. So that's another reason. And with ozone, it's similar to UV in that only about 10% of the source water treatment plants in the US use ozone. And that's, typically the bigger systems. Other benefits, is a pre-oxidizer. It can oxidize a dissolved iron and manganese to precipitate form. So this might be something that if you were looking to use UV and you had issues with iron and manganese, if you put this treatment before that could potentially pull that out, and maybe it would make your UV a little more effective. It can also destroy those disinfection byproduct precursors, the things that can combine with chlorine and cause DBPs. It's great for eliminating taste and odor issues or concerns, and it can actually help with coagulation, flocculation, if it's, occurs before those processes in our treatment train. How's it produced and fed? As I said, it's very, electricity or energy dependent. So we take oxygen, we pass it through an electrical field, a high voltage electrical field. It splits those molecules. So they start out as O2. It breaks them down into O2 and O3. They collide with each other and they become O3s. We've got this depicts some of what it might look like. And they're fed using a venturi or a fine bubble system. So, this type of thing where if you would probably need a good deal of space in order to do ozone. So what's the, ozone residual? What's the ozone cycle? So we started with we got the O2, we add energy to it, and it splits them off. And it creates these O3s. Well, these O3s aren't really stable, and they're looking to combine with other things. So that's why ozone doesn't usually last very long, because that's not an overly stable form. And so it attaches then to these bugs and kills these bugs, and it goes back into the O2. So, it's a cycle. It goes from O2, we add energy, we form O3, the O3 is good, it attacks the pathogens, and then we end up with O2 again. The residual, it has a residual, but it's a very short-lived residual. So it's nothing that we could expect to put out, into the distribution system and have it, get very far. So for the concentrations that we would need for disinfection, we'd want around 2 parts per million for disinfection. For oxidizing, those things like iron and manganese, 0.44 parts per million of ozone per milligram of iron, and roughly twice that, or 0.88 milligrams per liter of ozone per milligram of manganese. So we're going to switch gears, and I'm going to look at regulations. So specifically with surface water treatment, we have the surface water treatment rule. So we've covered some of these things before. We've talked about viruses and the need for 4-log removal. We've talked about Giardia and the need for 3-log removal. Crypto requires 2-log removal as part of the surface water treatment rule. Disinfection residual, leaving at the entry point or to the distribution system or leaving the plant, you typically want to see at least 0.2 parts per million, and you can't be over 4.0 parts per million. But I would assume if you've got a treatment plan, your regulating agency for treating surface water is going to probably want that to be closer to 1.0 parts per million at the entry point or leaving. Turbidity limits, combined filter effluent. So that's after it all comes back together, after all your filters come back together, of less than or equal to 0.3 NTUs. NTU is a measurement of the cloudiness, and it's the nephelometric turbidity. So that's less than or equal to 0.3 in at least 95% of your samples. If you're monitoring every 4 hours, and you're never allowed to exceed 1 NTU at any time. Part of the surface water treatment rule is a requirement for surface water systems to have sanitary surveys every 3 years. There's another one of those guides that I had mentioned. I would take, and if you're interested, quick, look at the quick reference guide that EPA puts out. Why is this not moving? All right. So this chart, it shows the maximum log removals or credits that your regulating agency can give you depending on what type of treatment. As we noted, conventional direct filtration are kind of the more common ones. We've got other ones here. Some of them, we had said that you need 0.3 NTUs with a max in your combined of 1 for these treatments, and they're a little less for some of the others. The credits given by the state are based off the type of treatment, the treatment train, and as part of this, disinfection residual should be monitored continuously in the distribution system entry point, that point where we're determining CT. So it also shows the minimum logs of inactivation needed for disinfection. So if we're getting 2.5 of our 3 from Giardia from our treatment, we're going to need a half from disinfection. And if we're getting 2 for viruses here, we need a total of 4. We need to get 2 more from chlorination. So those are the most common ones. Disinfection residual monitoring for small systems. How often do we have to do it? It's based off of population. And smaller systems are allowed to do it less frequent. So populations of 3,300, you're going to have to collect 4 samples a day at equal intervals throughout the day. A lot of small systems, the plants don't run 24 hours a day. So you were to run 8 hours a day, you'd have to collect them every couple of hours. So I want to quickly talk about the Milwaukee cryptosporidium outbreak. It occurred in 1993. There was a bunch of ice melt and rain upstream of a wastewater treatment plant. And that allowed for there to be, the treatment plant discharged and the water got to Lake Michigan. Well, Lake Michigan was the source of 2 water treatment plants, drinking water plants for Milwaukee. Each one of them, the north and the south, served about half of the population of 800,000. So these cryptosporidium cysts were in higher numbers. They were allowed to pass through the filters of the southern plant. The northern plant really didn't have any issues, and it caused 403,000 people to become ill, 4,000 hospitalized, and 69 dead. So this was a big thing. We talked about these cysts. They're hard to treat, and they're small. So what happened? They invest. Initially cryptosporidium, they didn't really even document it until 1976. They thought it was pretty harmless. The investigators for this didn't know what the problem was initially. Unfortunately, crypto has an incubation period of 7 to 10 days. That means that if you take it in on it'll be one day, it'll be 7 to 10 days before you even you feel symptoms or you're diagnosed. So it was hard to pinpoint, but fortunately the mayor decided to issue a boil water notice, and hopefully that staved off a bunch of more illnesses. One of the ways that investigators were able to find it is that they examined blocks of ice and were able to collect those samples out of it. So the ice was from before they had fixed the problem, so they were able to identify it in historically, because the factors, like I said, they had excessive ice melt and precipitation. They had some failures in the wastewater treatment plant. They had a practice of reusing some of the backwash water. And then at the time, the turbidity limits were not what they are now. Events like this, they lead to changes in EPA requirements. So the Milwaukee event resulted in the implementation of the long-term 2 enhanced surface water treatment rule in 2006. Similar things like this have caused changes. The issues that came out of Flint, Michigan, with lead and copper caused changes to the lead copper rule. So it's unfortunate when these things happen, but the hope is that we learn from them and we improve. So we're things are changing all the time. So in Milwaukee, the turbidity levels were normally below 0.25 NTU, but they rose to a level of 0.45 during March and April of 1993. And as we indicated, right now, 0.3 would be of concern. So they also had two spikes, 1.7 NTU and then 1.5. And even those at the time didn't exceed what was allowed. So, and, you know, when it happened, the turbidity of the filtered water couldn't exceed 0.5, which it didn't, and in at least 95% of the measurements, and it couldn't exceed 5 at any time. So, so it didn't seem like there would be a problem. But you know, we eventually figured out that the limits needed to be lower. So this just shows some of the, you know, the time frame for this. So this, the solid line is the southern plant that they had the issues with. They had a couple spikes. The northern plant, you know, was pretty consistent. So turbidity monitoring of the combined filter effluent. So we need to look at when our compliance is determined based off of what the turbidity is of all of our filters when they combine, and typically before they go to the out into the system here. So let's see, combined filter effluent, as we had said before, less than or equal to 0.3 NTU, at least 95% of the samples taken each month, with a maximum not to exceed 1 NTU. The combined filter effluent must be recorded at every 4-hour intervals. And the location of that is, you know, representative of the combined filter water. They want to make sure that it's not any one of the filters, that all of the filters are operating properly. And that's normally the pipeline where the individual filter effluents come together and combine and prior to getting into the clear well. Individual filter effluents need to be monitored continuously and recorded at least every 15 minutes. So at each filter, we have to have more up-to-date information on. That data doesn't have to be reported, but it needs to be kept on site. So you need to maintain it, but you don't have to report it. Summaries are often adequate, and you need to report. You're going to want to take, you know, report any corrective actions that you may have had with any of the individual filter effluent they may have had problems with. So if systems with only 2 filters can conduct continuous monitoring of the combined instead of doing each one of the individuals. If you get beyond 2, you have to do them individually and combined. And any corrective actions that you need to make, or, you know, to improve the performance, they need to happen if we've got 2 consecutive individual filter effluent turbidities exceeding 0.5 NTUs. So this depicts here where, you know, our locations would be. Individual filter effluent monitoring locations are after each one of the filters. The combined filter effluent location is typically after all the individuals come together and before the clear well. Sanitary surveys, so they're conducted by the primacy agency, and you know, it's a more in-depth, typically the primacy agencies I believe for us, it was quarterly to every 6 months, we'd be out to visit systems, but we only did these sanitary surveys every 3 years. So this was our real in-depth look at systems. So we want to identify any potential public health risks, may want to make sure the system has the ability to provide the quantity and quality of drinking water they need to provide. And it's an opportunity to educate system operators and provide any assistance that they might need. And you would expect that they're going to look at the entire plant and want to review all sorts of documents. So So the sanitaries surveys are required for surface water treatment plants under the surface water treatment rule and for groundwater systems under the groundwater rule. As I said, they're every 3 years. Non-community water supplies can be up to every 5 years. And then, treatment is one of the elements of a sanitary survey. There's several different things that the regulating agency will look at. They're going to review those individual and combined filter effluent turbidity monitoring records. They're going to look at your different processes that you have in your treatment plant. They'll look at the chemicals you add, what your dosage is, how you feed them, how you store your chemicals, what's your what do your disinfection monitoring look like, and your log treatment records? Are how are those records comparing to what you're supposed to be having? What's the condition and the capacity of your plant? Are you able to provide the proper quality of water? And then, is your plant deteriorating? Is it in good shape? Are you doing maintenance? Do you have any cross connections? Is your cross connection program up to snuff? Are you utilizing the proper backflow preventions? Your process control monitoring. Are you looking at the operations of your plant and how it's performing? Are your lab testing practices what they should be? And then, are your operators certified? Are they trained? Are they knowledgeable to do the job they need to do? So, what's the process? Prior to the survey, you want to make sure that you've got all your records together. They're available, and you're prepared for the inspector to come and do a tour of the water system. They'll typically do a tour of the entire water system from throughout the entire plant into the distribution system. Look at any tanks or pump stations you may have. And after the survey, they're gonna write a detailed letter, and it's gonna tell you about any of the findings they have. If there's any deficiencies, you'll know right away, and they'll give you a timeline to correct those. So there's 3 different categories of deficiencies. The most urgent and important are significant deficiencies, and those are things that could introduce contamination and potentially harm the public. Moderate issues that they're not immediate, but they could lead to problems, so they need to be addressed. And then lastly, minor. So these are less serious. They're probably issues that, things that should be done, but they're not overly urgent, but it would probably help you operate your system a little better. So now we have my final poll. Which of the following is an accurate component of surface water treatment rule compliance? A, turbidity must be equal to or lower than 1 NTU in 95% of samples. B, turbidity must be between 0.3 and 1 NTU in 95% samples. C, turbidity must be equal to or lower than 0.3 NTU in 95% of samples. And D, turbidity measurements are not required if inactivation exceeds 3 log. All right. Thank goodness we don't have to do any calculations on this one. Oh.
As they finalize their answers there, Daryl, how long of
Yes.
a break did you want to lead into here? 5 or 10?
I don't want to press Greg for his time, but how about we we'll take 10, but we'll end the poll at the end of 10 minutes.
Yes.
Sounds good. So we'll go ahead and start the 10-minute timer now. And if you still want to take some time on the poll, that's fine. We won't close it until we come back from break. Welcome back, everyone, from break. I hope you had a good short break time away. And we'll get started here.
That's my bad. I
All
didn't
right.
make the timer stop.
So, Lori, I think we end the poll. It looks like we have 60% saying C, 16 or 23% A, 16% B, and nobody said D. So the answer is C. Turbidity must be equal to or lower than 0.3 NTUs in 95% of the samples. So we will allow Greg to take over.
Hello, everyone. How is everyone doing? Hope you're enjoying the training today and that you had a great break. Thank you, Daryl, for that wonderful presentation. I wonder if my slides are showing.
Yes, they are.
Okay, great. So we left off yesterday. Get here with we were talking about filter ripening, and we were about to talk about filtration rates, and we'll talk a little bit about optimization and kind of tie everything together that we've been talking about. We talked about how when a filter run first starts, there's a little spike in turbidity. And that's the filter ripening period where those grains of filter media become coated with coagulant chemical, and then the filter can begin operating at its optimal level. And so normally what we'll do is filter to waste during those first few minutes. In this particular chart, the first about a minute and a half to 2 minutes had a spike, but it can take a little longer. It can take 10, 15 minutes or even longer. Now we're going to go in and they're going to talk about filtration rates and backwash rates a little bit. The rate that a filter can operate ranges from about 2 to 10 gallons per minute per square foot. So if you think about a square foot, you think about this is an area, surface area, a square that's 12 inches by 12 inches, and you imagine pouring 2 gallons over that 1 square foot area over a minute's time. That's the low end of the scale, and then the high end of the scale would be 10 gallons per minute. But the typical rate for a rapid sand filter is probably around 5 or 6. And you can see the water being applied. And this filter bed has different layers in it. We can see, we're going to talk about that a little bit. Here is the filtering mode. You see that there's a backwash outlet and a backwash inlet, and there's a closed valve indicated by those red boxes with X's in them. Those are closed while we're filtering. The water is coming in from the top and trickling down through the media, and particles are being captured in the media, and it goes out the filtered water outlet, and it's going to be traveling toward that disinfection basin that Daryl was just talking about. When we're in the backwash mode, you notice the inlet pipe, the raw water inlet pipe to the filter is closed, and the filtered water outlet to the disinfection chamber is closed. And we now have clean water coming in through the backwash, and it's going up to the media, and it ends up in a trough, a backwash trough. It's captured there, and it continues on to the backwash outlet, where it goes to probably a pond where it's captured, and that sludge will be allowed to dry. A couple things to think about here. In a gravity filter, the backwash is usually initiated when the head level increases to a certain point, and what we're talking about there is the water that's above the filter when it's filtering. When the media becomes clogged, that water level will rise because the water can't get through. So that is a direct measurement of the depth of that water. Also, when we're backwashing, the media expands. If we had a media level that was equivalent to this blue dotted line we've just drawn across, during backwash, that would expand a certain percent, somewhere between 20 and 50%, depending on the media that we're using. Sorry, and it will expand so that those filter particles will come apart and allow those particles that have been trapped between the media, they'll be able to be washed out. In a pressure filter in a tank, we'll usually initiate backwash with the pressure differential between the water coming in and the water coming out. It'll get harder for water to come in, and the pressure differential will be larger. There's a couple of tips we want to talk about, or factors we want to talk about with backwash here. Um, Backwash is faster than the filtration rate because we want to dislodge those particles and we want to fluidize the media. So we're fluidizing means expanding the bed somewhere between 20 and 50%. Also something to think about, if you're backwashing when it's colder, when you have colder water is more dense. And if you're backwashing at the same rate that you used in warmer weather, you could actually lose media. So you might have to adjust the backwash flow or the backwash rate when it gets colder. And it's affected by the type of media. Less dense media can be expanded more easily and you could lose that media more easily, while the more dense media, the media with higher densities, they require higher rates. And over time, if your backwash rate is too low, it can lead to basically the accumulation of all these particles of clay and particles that aren't removed, and it can lead to mud balls. And there's two problems with that. A mud ball in a filter it takes away some of the filter capacity, but it can also lead to cracking, where there's a crack that occurs in that mud, and untreated water can just pass right through the filter. If it's too high, of course, you'll lose media when you're backwashing. I'll give you an example of a filtration rate calculation here. Our formula for filtration rate is pretty simple. We calculate it according to the flow coming into the filter, and we divide it by the area, the surface area of a filter. And so here we have a rectangular filter. It's 10 foot wide, 20 feet long, and it has a flow rate coming in of 1,000 gallons a minute. And so we're going to ask, what's the filtration rate? And we're going to use gallons per minute per area and square foot. We first of all calculate the area. 10 foot times 20 foot gives us 200 square foot. And we already have the flow. So we're going to take that flow of 1,000 gallons per minute and divide it by the area. And we see this particular filter has a filtration rate of 5 gallons per minute. And we're going to have a chance to do one of these in a moment. Now let's look at a backwash for this same filter. And we're going to switch things up a little bit because we already know the backwash rate we want to attain, but we don't actually know the flow that we need to get to that. So let's look at that here. We have the same filter. It's 10 by 20. And the flow is going to be coming up through this filter during backwash. And we're going to ask, what flow do we need to attain a filtration rate of 15 gallons per minute per square foot? So I'm going to show you the formula that I would use here. We know the backwash rate is the flow divided by the area, but we don't know the flow. We know the result that we want. We know the backwash rate that we want. Now, this is a little bit of an algebraic manipulation. The left-hand side of this equation has flow divided by 200 square foot. The right side of the equation has our result, 15 gallons per minute per square foot. What we're going to do is multiply both sides of that equation by 200. In the left-hand side, it'll cancel out. And in the right-hand side, we'll have 15. Did I say divide? I meant we're going to multiply both sides, if I didn't say that correctly, by 200 square foot. And so on the right-hand side of the equation, we have 200 square foot times 15 gallons per minute per square foot gives us a total flow of 3,000 gallons per minute. And this is a very realistic equation that you need to do to determine what flow do we need to properly backwash this filter. So we're going to have a chance to do this now. We have a filtration rate here. We have a gravity filter. It's a little bit different dimensions. It's 15 feet wide and 25 feet long. And its flow that's coming in is 1,200 gallons per minute. So let's calculate the filtration rate in gallons per minute per square foot. Daryl really covered a lot of topics there in his discussion, and he covered compliance of filtration, the final effluent, the combined filter effluent needing to be below 0.3 the majority of time. We'll talk about turbidity measurement in a moment, but initiating the filter at the right time, being aware of that initial spike in turbidity, and then ending the filter run at the right time. Those are all, and having the right rate of backwash will help the filter run at its optimal level and help you to at least achieve that compliance goal and maybe even optimize goals. We'll talk about some optimized goals in a moment here. I was pleased to see the wide variety of where people were coming from in the last couple days. I see you're all, great majority of you are doing very well on this problem. I'm going to show you an example of a technical assistance situation that project that Daryl and I worked on together as well, where we actually had to calculate the filtration rate and the backwash rate. It looks like the responses have significantly decreased in their frequency. Lori, can we move on?
Sure. I will share the results.
So 91% of you chose answer C, 3.2. When we look at the solution here, first of all, we'll calculate the area, 15 times 25, of an area of 375 feet squared. Then we have all the information we need now. 1,200 gallons a minute divided by 375 square feet, 3.2 gallons per minute per square foot. So there's our filtration rate, a little bit on the lower end of that 2 through 10 scale. And turbidity monitoring it's good to do at multiple points. It's good to know what your source water turbidity is, because that could be changing, especially if your water source is a river and you're experiencing precipitation events. It's a good idea to grab turbidity samples from the outlet of the sedimentation basin, because you're almost to the filter, so you'd like to know what's happening before the filter. And then, of course, after the filters is you're taking samples there anyway for compliance. So if you can line up all those and then combine that with some of your other data, like the zeta potential, what's the balance of charges between the coagulant and the particles, and then conducting jar tests, and also measuring pH, temperature, and alkalinity might give you insight into changes that are occurring. A turbidimeter works by shining light through a sample, and we're actually measuring the amount of light that's scattered at a 90-degree angle from the light path. And that light that's scattered is due to particles that are in the water, even small, very small colloidal particles. And this helps us to be able to detect that they're there. It would be very difficult to detect them otherwise. And if we did find a way to detect them, we'd have to do a very involved laboratory process that wouldn't give us real-time results. But a turbidimeter gives us real-time results, and it can detect those very small particles. And if you see, it's there's an arrow pointing straight up. That's the reflected light at a 90-degree angle, and it's being detected by a light detector. They call it a photo multiplier tube, or a silicone photodiode. It collects it measures the intensity of light, and that light is due to those particles. And you see, I've put some particles of different color. Color can affect how well a turbidimeter works. The recommended or the required to a certain extent type of lamp that's specified in EPA, although it's slightly changing a little bit, is a tungsten filament lamp, and it heats up and emits a light. And it's, if you look in the EPA turbidity methods, a tungsten filament lamp is mentioned. It creates a spectrum that goes beyond just visible light. It dips a little bit to the left in ultraviolet and quite a bit to the right into infrared. But across that visible spectrum, it produces all of the colors, which makes it a good light for detecting particles in a sample. There's all of the, not just one color is available, which could be absorbed. It has all the different colors. There's other options here that are kind of still developing. Some of these are approved, and some of them are still not approved yet. Some of the models, but you can use a LED lamp that produces an infrared light, invisible, and it makes it less sensitive to absorption for color particles. There's also laser diodes that offer some extra sensitivity for very low turbidity. And there's even dual LEDs where you have a white light and an infrared light to kind of compare and contrast findings between the two. The white light might have some reflection or absorption where the infrared wouldn't be affected by that. The turbidity device that you use, there's online turbidimeters, and there's the kind where you can put a sample in, like a lab desktop type of a model. Both of them would be required to be calibrated, and calibration is based on a chemical called formazine, and it produces a very stable turbidity standard. If you it starts out with a higher amount, but you dilute it down to 40 NTUs or nephelometric turbidity units, and then you can even dilute it down farther to whatever you'd like to compare it to. It helps you to calibrate. There's a couple chemicals that, if you want to make the suspension in the lab, there's a couple chemicals that you mix in a very specific proportion, and there's also options where you could purchase this standard as a pre-existing compound or mixture, and then you just have to dilute it. We've talked a lot about jar testing, but we haven't really gotten much into it. But basically, jar testing is a lab process where you can simulate the treatment process. It starts out, you add your coagulant dosages, and you usually spread out the dosages. I gave an example here. You might have one jar with a 5 milligram per liter dose, another jar with a 10 milligram per liter dose, and so on. You see two different models on your screen. One has 4 jars and the other has 6 jars. The 6 jars would obviously give you more range. And as you get closer to the dose, let's say 10 milligrams per liter was the best in our first example here. Well, we'd probably want to hone in on that a little more and maybe do something like 8, 9, 10, 11, 12, something like that, so we could narrow the range, so we get a more specific dosage. So we want to find the best dose that gets us the best settling and the best clarity of water. Then we would, in step number 2, we would actually simulate the flash mix with really high speed mixing, and we might do that for 30 to 60 seconds. Then we'd simulate flocculation by having a slow, gentle mixing speed for possibly 30 minutes. And then we'd allow these jars to settle somewhere between 30 minutes and an hour. That's simulating sedimentation. Then we'd observe what jar has the clearest water, what jar has had the best settling. And some of the jars, if our ideal dose was right in the middle, some of the jars will have too much and others will have too little. If not, we'd have to redo the test with a different range. And so this is something you'd want to do if you had changing water conditions. And you can also use this to test pH adjustments, alkalinity adjustments, and so forth. You can test more than just coagulant dosage, and you could compare performance of different coagulants to each other. And this image here shows source water can change radically, especially when there's precipitation events. And here's a diagram here that kind of illustrates graphically what we were talking about: monitoring the source water, monitoring the settled water after the sedimentation basin, and all that combined with our final turbidity measurements can give us a good picture of what's going on. And if there's problems, it'll help us to determine where we need to start looking. And with that, segues us into talking a little bit about water treatment optimization. And this is generally about trying to get your plant to function at a level that exceeds the regulatory compliance standards, and it gives us better health outcomes, and gives us a little buffer too between compliance and non-compliance. And here's an example. We might shoot for a finished water turbidity of 0.1 NTU rather than 0.3. We might shoot for total trihalomethanes to be below 60 parts per billion instead of 80. A turbidity of settled water after our sedimentation basin, we might shoot for something between 1 and 2 NTU. That would be a process control in the middle of the process. So what we're doing is to get there, we're going to compare what our plant performance with some benchmarks and develop some key things that we want to measure to let us know if we're getting closer to that goal. For example, if we want to achieve a goal of 60 parts per billion total trihalomethanes, that's our benchmark. One of the key performance indicators might be the level of total organic carbon that we're removing in our process. Here's some data from EPA in regard to the Compliance Assistance Program, optimization program that's nationwide. And you can see between 2019 and 2023, they've reduced all the plants that are participating in this have reduced their TTHM levels from pretty close to 80, which is just below or above, in some cases, the compliance limit, down below that 60 parts per billion level, just like we were saying. So water systems are succeeding at doing this. And here's an example here of how they are meeting turbidity levels. The red line is the actual turbidity, the 95th percentile turbidity. And we're starting over on the left-hand side with turbidities just under 0.3, like 0.27, 0.24. And on the far right of the screen, the red line, we're getting down to 0.11. We're getting close to that and 0.1, we're achieving that 0.1 NTU. The blue line is the percent of measurements that are meeting that 0.1 NTU optimization goal, and we're getting we went from 71% all the way up to 91% in this period. These links here on your slides will take you to these optimization resources. There's the EPA optimization program. There's the link. There's AWWA has a partnership for safe water that you can join. And then finally, there's another one. There's also many at the state level, but this Association of State Drinking Water Administrators, they also have a site where you can look and you can get some ideas and some guidance on how to start this process. And there's some optimization strategies I want to talk about. The first one starts with daily water quality measurements of our raw water. So first of all, we would want to measure, for example, our turbidity, our raw water turbidity, and that would give us a baseline to compare our removal rates to, but it will also let us know what are the changing conditions that we need to prepare to react to. So the second one here is measuring that settled water turbidity. So we're looking at the outlet from the sedimentation basin. How well has our sedimentation basin been working? We talked about yesterday that we're looking between 60% to 80% removal of turbidity in most sedimentation basins. And that's a wide range, but that's the range that that water plants are achieving. But really, these optimized goals that we're looking at here are closer to 90% efficiency of the turbidity. removal in a sedimentation basin. So the idea is here, how do we measure this? Well, the recommendation is to take settled water turbidity measurements every 4 hours from each of our sedimentation basins, and we compare it to the following goals. The first one is trying to achieve less than 1 NTU 95% of the time when our turbidity is lower at 10 or below, and trying to achieve less than 2 NTU when our turbidity is greater than 10 NTU. And so how do we get there? Well, let's talk about how would we get our sedimentation basin to perform. And there's a number of things I'm going to share with you. First of all, we'd back up and start with the dosage process. We'd conduct additional jar testing and try to narrow that range of dosages. Try to calculate that dosage a little bit more precisely. And we could also jar test for different pH ranges. We could jar test by adding polymer to our coagulant and even alternative coagulants to see what gives us the best results. We should also measure different parameters like temperature, alkalinity, pH, and the flow rate. If we had an increased flow and increased temperature, that would give us different conditions if we had decreased temperature and lower flow rates. If you want to learn more about this, I have some links in each of these slides. There's a jar testing tech brief, and there's a document called Jar Testing Made Easy. The first one's cuts to the chase, and the second one gives you kind of an expanded instructions about jar testing and about more than just coagulants too. So it's a good document to have. Also, we'd want to calibrate our equipment. If we do all that work to jar test and get our precise dosage that we want, it doesn't do us a lot of good if our chemical feed equipment isn't delivering that dose. So you see the images on the left, the female operator that's testing. She has a calibration tool on the right of that image, and she has a source of liquid that she's running through that metering pump, and she's trying to see, is the dosage accurate and consistent. And you can see one of the devices on the top left of the screen, that a graduated tube that you can use to measure the dose that's being delivered. Also, a streaming current meter could be a good addition, and I'll talk about that in a moment here. But there's also some resources here. Calibrating liquid feed pumps tech brief, and then there's a chemical feed pumps and calibration that was created by the Department of Environmental Protection in Pennsylvania. It's a good document. I would suggest adding these to your library. Now, the streaming current meter, it's similar to measuring zeta potential like we talked today, but this streaming current meter is always online, and it can be set up to dose the flow. It can pace the flow of the coagulant. So imagine the operator says, "Oh, I need to take a break," and the operator goes outside for 10 minutes, and during that time, the turbidity radically changes. Well, the streaming current meter would just adjust the flow of the coagulant dosage. So it can help you to pace the flow. There might be some hurdles to go through because there are some things that will cause this to not give you as accurate results. For example, if you're feeding a bunch of lime to adjust pH, that could affect the probe. So the water quality could affect the accuracy of the probe. But basically, the output. I mean, if you see at the bottom there, this flow signal controls the coagulant feed, and that is going into the flash mixing process. Just downstream, if you look on the right-hand side of your screen, that image on the bottom, to the right of that, the water is flowing out of the flash mixing process. Just shortly downstream, you have your monitoring point. You want it as close as possible to that. Obviously, you don't want it right in the flash mixing compartment, but just downstream of that, that'll give you a good idea it'll give the machine a good measurement of what is the balance between the negatively charged particles and the positively charged coagulant. So there's also some resources for this. Streaming current meters used to optimize coagulant dosages. That's a little case study in water world of a utility that actually used one of these, and it tells about some of the hurdles they had to go through, and how it eventually helped them to save money in overdosing and to respond to changes in their turbidity. And the second one, the basics of streaming current detectors. Um, it's by a vendor, but it gives a good overview of how they're used. Also, we're still talking about getting that settled water turbidity down, and we're backing up to the coagulation process. We also want to evaluate how efficiently are we actually mixing the chemical. And there's two concepts. First of all, there's the contact time. How long is the liquid and the coagulant allowed to be in the tank to be mixed? That's the contact time, and generally that can range between 10 and 90 seconds. If you don't have enough time, you're not going to get enough mixing so that the coagulant touches every particle. Also, a mixing intensity. You want to have a high mixing intensity in the flash mix. So something to also consider is the inline mixers. We talked about those yesterday. That can help you in one major way, is because if you have a tank and an impeller like we see at the top right of your screen, there can be dead spots depending on the shape of that tank. And there's a 10 state standards document that provides some good information on how to evaluate our mixing. And so one of the things they mention is a mixer should provide a mixing intensity of at least 750 feet per second per foot. And that is something that you can talk to your vendor about. They have some calculations that they use that are specific to certain kinds of impeller blades that would help to choose that. We also want to evaluate the mixing of our flocculation basin. And there's a couple standards here also from the state standards. We want the detention time of a flocculation process to be at least 30 minutes, and the intensity should taper off as the water travels through the process, because we have larger, more fragile flock. We don't want to damage it. And the actual velocity through the basin, it shouldn't be less than 0.5 feet per second, because you don't want the particles to settle out in the tank, but you don't want it greater than 1.5 feet I'm sorry, 0.5 feet per minute, or greater than 1.5 feet per minute. Because you don't want them to settle out, and you don't want to have a lack of detention time, or to go so fast that it's causing problems with shearing flock. And the peripheral speed of the mixing paddles, and this is actually the tip speed. If you looked at the outside of a spinning propeller or a mixing paddle, the outside is going faster than the inside. And that speed should range between about 0.5 to feet per second to about 3 feet per second. You can imagine the 3 feet per second would probably be in the initial paddles where you have faster mixing speed, and the 0.5 would be closer to the final paddles. Also, when you pipe the water from the flocculation basin to the settling basins, the sedimentation basin, the flow should be within a range too, between 0.5 and 1.5 feet per second. You don't want it going so fast that it's causing agitation. Also, another thing to evaluate is there settled material in the basin that would give us could contaminate our water, or it could be evidence that we're not mixing effectively. Also, you want to look at the baffling between the cells. There usually be some kind of a wall with a bunch of holes in it that prevents short circuiting and helps to make sure there's sufficient mixing. So you want to evaluate the baffling system. And here's some articles here. There's a article about coagulation and flocculation process and mixing essentials, and there is the 10 state standards document about flocculation mixing. And evaluating the sedimentation basin itself, all those things we calculated yesterday, overflow rate, the weir overflow rate, and the detention time, you can calculate those and compare them with the design specifications for your plant. You also want to inspect the baffles and the inlet and outlet conditions to make sure there's no excess velocity currents. And also inspect the sludge removal equipment, because if you're not getting complete removal of sludge, it could be leading to having problems with turbidity. You can also consider some modifications, such as adding tube or plate settlers and adding baffling to improve the performance of the sedimentation basin. And there's a couple of great documents here. Sedimentation and Clarification from the state of Oregon. Very good document. And then there's a little article here about plate setters versus tube settlers. And that might be worth reading. Basically, plate settlers work better. They're harder to install. Tube settlers are easier to install. Don't quite work as good because they restrict the flow of the water. Filter optimization, we'll talk about the goal first. The goal, we mentioned it already, is for filtered water turbidity to be less than 0.1 NTU. That's the optimized goal, 95% of the time. And we're not talking about the backwash and the filter ripening period. The maximum level, instead of being 1 NTU, is 0.3. That's our optimized goal. And the minimum filtered water turbidity following backwash is also less than 0.3 and returning to 0.1 within 15 minutes. That means we have to have good backwashing processes. And of course, the first step to have your filter working well is to make sure all the things that happened before it is working well, the coagulation, flocculation, and sedimentation processes. I'll show you a couple of things that you can do. The first is a filter inspection. You can actually, you see the gentleman on the top right of your screen, he has a filter judge. It's kind of like a sludge judge, but it's a long tube that captures a core sample of the filter. It captures all the layers in the filter. You push it down all the way to the support gravel, and you bring it back up, and you can analyze the sample. You can make sure that the filter beds, each layer has the right amount. We haven't had media loss. You can look to see if there's any mud balls or impurities that have been collecting that would indicate we're not having good backwashing. If you have uneven or mixed up compacted or loose media, it could mean you have underdrain issues where the water from backwash is not flowing at an equal flow in all spots. There could be a broken nozzle, or there could be a clogged nozzle. You also want to observe the filter during backwash. If there's places where there's boils, like boiling water, there's too much water coming out there. And if there's no action at all, it means there's a dead spot. There could be broken piping or blocked piping. Now notice in the picture on the photograph on the upper right, do you see the backwash troughs? There's water in those troughs flowing. That means that this person is taking the sample when the media is fluidized, and they're able to push that sludge or that filter judge down through the media a lot easier than to capture a sample. You also might want to collect some of the sample for lab analysis. You can look at the media size. Over time, the media will get worn out and it can become too small over time. The rule of thumb is every 15 years to change the media, but it might be sooner or later. The media can also become fouled, and you might need to replace it. And there's a couple of good documents here. One from Texas, all about filter assessments. There's an article about core sampling. It's a vendor. And then there's some an article on considerations about refurbishing or replacing media. So those are all good sources of information for you to check out. So improving the filtration process, you want to first evaluate the filtration and backwash rates and compare them to the specifications. If it's too high, you're going to lose media. If it's too low, you're going to have a clogged filter. And you want to observe the backwash also. You can actually measure the amount that the media is expanding. And to learn more, there's 3 articles here. Optimizing backwash and filter, and how to perform a filter inspection, and even a self-assessment document that will help you. And also I wanted to give you an example about a project that Daryl and I worked on. We actually used these equations to help evaluate a plant that was using oxidation filtration. That just means adding an oxidant to cause dissolved iron and manganese to precipitate, and it's very much like the treatment process. It causes the dissolved particles to become precipitate particles, then you can filter them. And there's common oxidizers, chlorine, potassium, permanganate, and ozone. We could also use these for pre-oxidation of iron and manganese and other things that we want to oxidize before coagulation in our surface water treatment plant. And so we actually calculated the filtration rate. We had a filter that was 3 foot in diameter. It was a pressure filter, and we knew the flow. And so we calculated the area of the filter and divided it by the flow, and we found out the filtration rate was 5.03, and the upper limit was actually 5 gallons per minute for this filter. So it was right at the max or a little bit over, and the backwash rate turned out to be 12.03 gallons per minute per foot. And that was also a little bit either at or a little bit above the minimum backwash rate for that particular filter. And so this plant was having problems, and so they were right at their max on both. I'm going to skip this one here, on both the backwash rate and the filter rate. So just to wrap this up here, we're at time right now. Reducing disinfection byproducts, Daryl talked about that. If we look at our optimized goals here, less than 60 parts per billion and less than 40 parts per billion for TTHMs and HAA5s. How could we get there? Well, some of the things have to do with optimizing the removal of those small organics. We talked about charge stabilization using alum, for example, at a low pH to remove those small particles. And one of the ways we can monitor the effectiveness is by measuring total organic carbon. We want that ultimately in our finished water to be below 2 milligrams per liter. So we want to monitor TOC in our source water and our finished water. So we're enhancing the removal of particles. And also we want to enhance the disinfection process. We don't want to use more chlorine than we need to. We want to make sure we meet our CT compliance inactivation goals and have an adequate residual without creating disinfection byproducts. So this kind of ties removal and disinfection together here. And there's a great document, I think Daryl also shared this, disinfection profiling and benchmarking manual from US EPA. And this is an excellent document to have in your library. And let's skip the poll here for now, Lori. And today we're finishing up. We covered a wide range of topics from source water to removal processes to disinfection to regulations. And finally, we ended up with optimization. I'm sharing a couple of links here. There's a couple of links here. This is a Georgia inspired training. I'll just say it like that. And so I'll share a couple of links here. We have a link that goes to a Georgia Water Quality Standards page. There's a document here, the minimum standards for water systems in Georgia. And then also I want to share an IB Environmental link. It's an organization that's here in Georgia that organizes trainings for water managers, and they help to connect water systems with funding sources as well. So that would be a good source for you. And if you don't remember anything else today, we want to think about the 3 big things we learned. Disinfection is the inactivation of pathogens that's achieved through a combination of disinfection concentration and contact time. Removal processes include coagulation, flocculation, sedimentation, and filtration. And this is all about destabilizing those very small non-sellable particles and pathogens and causing them to clump together so they can we remove them. And then compliance is achieved by a combination of both these things. We are ensuring turbidity limits so that we know that we're removing matter from water, and we're achieving an overall log treatment level through a combination of removal and inactivation. So I want to thank you everyone for participating today. I went pretty fast. I hope I didn't go too fast, but if you want to share your thoughts today in the chat, was there something new you learned? Did you enjoy the training? What parts of the training created more questions than answers? And what can we answer or clarify or expand on? I'm going to turn it back over to Lori and Daryl. Thank you.
Okay, thank you, Greg. As we head out here, I just want to call your attention to that. I did put the link into the chat for anybody who needs a certificate of attendance. I'm going to drop it in there again, just in case you didn't see it. There it is again. And I do have a question for Daryl, if you don't mind, Daryl,
Yep.
coming up. And the question we had for your time was from Brian, and he asked, what are some advantages or disadvantages of dry chlorine pellets?
So HTH or calcium hypochlorite. So some of the advantages of it would be the fact that, in comparison to gas, it's, gas is not very portable. Gas can be extremely dangerous. So you don't have those concerns. One of the, some of the big concerns with liquid chlorine is it's not overly stable. So through time, your concentration will dissipate. So I've seen, 12.5% chlorine solution after, given a several months, it could be down to 10%. So liquid chlorine doesn't usually hold that, it's not as stable. It tends to dissipate in concentration. Some of the benefits of HDH or calcium hypochlorite are the fact that it's portable. You can carry it around in buckets. It's not going to, it really shouldn't spill per se. So it's, it doesn't react until it hits water. So, it's much more stable. It's portable. It can, I understand that the cost is, it's a little less costly. So yeah, there's benefits and detriments to any of these. So I guess that's what I would say about HDH. I don't know, Greg, do you have anything else?
Just difficult to feed. I've
Yeah.
actually seen some systems that used a pellet, a tablet type of a system, and it was an erosion style. It worked fine, but it would get wet then dry and then not erode to the same level. I wanted to say a quick thing. If even if you're not getting a certificate, we'd still appreciate if you were able to fill out the end of course survey, because there's an evaluation in there as well. So if
Yeah,
you
we get good information from that. We appreciate if you guys can take the time to do that.
Yes, absolutely. We do value your input on that. And but please make sure that if you are expecting a certificate of attendance, that you do grab that link out of the chat. And if you happen to miss it and you have to run someplace else, you're welcome to email us at ctt@mtu.edu and we will get you that link. But just remember, it expires in 24 hours.
Hey, Daryl, there's another question here in the Q&A. What about pellets into the well casing? I actually saw one system that did that and it worked fine. They had a feeder that placed pellets right into the casing. Have you seen that before?
I've never seen that. Yeah, I don't know. I guess so you're Greg, you're saying that the feeder put it right into the well casing. Was that, what happens if the well's not running?
It
Was
wouldn't
that
operate.
paste?
And yeah, it was paste. It would come on when the well pumped. Yeah.
Yeah, I don't know. I think that, and for a situation like that, liquid chlorine would probably be as good or better of an option. But the thing I'd hate to see is somehow you ended up sending pellets out into your distribution system. Nothing like getting a glass of, chlorine pellet water.
So we have a question from Stephen. How could you collect source samples, raw water?
It's coming into your plant, so it's going to be at the inlet just before the coagulation point.
Yeah,
so you could even create a sample tap right there, right, Daryl?
Yeah, and true raw water samples should be for any sort of treatment. So.
Oh, we had a clarification there in the chat with the pellet feeder in play. How would you collect source?
Yeah, well, I guess that's a good point. It'd make that difficult to get a raw water sample. I don't know, Greg, what did they do? They stop feeding?
Oh, I see.
Sample.
I see what Steve is saying. He's talking about how could you collect a raw water sample in the well? Sorry, Steve,
From
I
the
missed
well.
that. Yeah, so yeah, that would be tough. But I mean, I don't know the situation. I only know of one time when they did it. One little system in Southern California when I was doing technical assistance there, they did it, and so that's a good point. I mean, you'd never know if you had coliform bacteria coming into that well because you'd always have disinfection residual in there.
I mean, I guess the whole point of it would, in my thought process is the only reason you do it is if you had a well that had, coliform issues or something like that. Because you're trying to get to it. Usually they end up trying to chlorinate on occasion, just chlorinate the well with liquid chlorine and pump it out, but yeah, I had never heard of that. Ryan mentions, the potential to rust out your casing and deteriorate components. You put it right into the well. Could have an effect on your pump. All right. Well, we appreciate everybody out there, and if you have questions, feel free. If you have the time to sit with us, and you've got a question, please do it. If not, I totally understand. You get on with your day.
How does the hydrologic cycle impact surface water quality?
Well, I mean, the cycle itself, I think, the process tends to, as water goes, evaporates, it usually clears up most things. I mean, the cycle is going to be the cycle. You get the potential every time it rains, there's a potential to add, whether it's from atmospheric from the air or pick up stuff on the ground. You always have the chance to add to it, but the cycle, I think the cycle tends to clean itself out. What do you think,
It,
Greg?
I was just thinking, I was looking at both sides, the good angel and the evil angel on my shoulders here. I mean, it evaporates out of the ocean, for example. It leaves all those impurities behind. You have pure water. But let's say it rains on that watershed you were showing us yesterday, and it flows past a cattle ranch and industrial. So then it has runoff right into the. So it's the old double-edged sword. But we wouldn't have any water if it wasn't for the hydrologic cycle. It keeps on cleaning it and dispersing it all around. Isn't it amazing that, like, for example, the Mississippi River, it's huge. It flows. It never stops flowing. That's because there's always water being taken from lakes and oceans and streams, and precipitation occurs up north of that river, and all the rivers that continue to flow, except for the ones right now that are supposed to be serving Arizona and California and Nevada. Good question from Moses. How do you ensure the continuous operation and monitoring of your disinfection system to prevent non-detectable residuals?
So, I mean, as far as to avoid that, I would think you'd want to have, you have some redundancy, you have pumps available, you monitor it. The operators are huge in making sure that plants operate properly. And so if you have attention to your operations, you can have sensors that, are monitoring stations and throughout the process that would alert you if if that was, if the residuals or the application was getting low.
Yeah, I like that. You know, it's a good question. Because when if you are let's say you're operating your system and it's always a 1.0 milligram per liter every day, and all of a sudden that drops, and you go out and you check everything's working, the chlorine pump's working, and it drops to 0.1 or 0. What has happened, Daryl?
All right, is there a source of contamination? Is something in there that's, taking up that chlorine? You don't have, it's combining and, that's the bad side. I mean, I think that would be the worst thing that could happen. There's always the potential that your pump's not, it appears as if it's operating the same way as it was, but you could check that with your tank to see if it's actually, if you're measuring it in gallons or you're measuring it in pounds, is it actually is the right amount going out? Yeah, I guess that would be my thought process would go to, there's something that chlorine is reacting with.
At a treatment plant, they'll usually have a continuous monitoring, and
Yeah.
you'll have a readout, and you might even be able to have an auto dialer on one of those. As far as in the distribution system, that's a little more difficult. I mean, you need to
Oh,
get
yeah.
around, and I think it's a good idea to know the key spots. I mean, maybe there's really, instead of like 100 spots, maybe there's really only 3 or 4 key spots to monitor chlorine, to know that things are going well, like in the farthest reaches of the system. Maybe there's 3 or 4 spots that are kind of more distant that you could check and get us, and be assured that we're doing good here. There's no contamination between the treatment plant and the far reaches.
All right. EFCN for EPA Region 6. Jeez. Let me see what. That was yesterday's. Let's see, EPA Region 6. Well, New Mexico is in Region 6, so that would be the University of New Mexico, the Southwest EFC. Yeah, we can, they're actually, let's see, there we go. Thank you, Ingrid. We got it. So, University of New Mexico, Southwest EFC is actually the leader of the EFC network. So, I would start there. They have a great deal of information online. They, like I said, they head up a lot of what we do. So, we, I'm sure that we could get you contacts there. You want to send, let's see, the other thing we could do is we could pull up the slide that shows let's see our information. So you could contact us at gliic-support@mtu.edu. You can call. Oh, did that not work?
Yeah. Hold on just a sec. That does, and then.
Oh, it's the
There's
next
all-
slide. All
there's-
right. So yeah, so there's information on contacting us. If you want to reach out, we could help you with that. like I said, they have a great deal of information online. So if you were to search for them, I'm sure you'd find, you look for their the group that handles the drinking water for them. They have a group, I believe, that does drinking water and one that does wastewater. So hopefully that helps. No problem, Richard. I hope that you get a hold of them and you get the information you're looking for.
Here's their
There you go.
homepage. You see that link, Richard? Are you still there? That's that take you right to the Southwest EFC.
Okay,
Alright.
so I don't have any additional questions that I logged throughout the training. If anybody who's still on has anything, please do go ahead and put it in the chat. We'll probably hang out for a couple more minutes, just in case.
Thanks for all your help today, Lori and Ingrid. And thank you for the excellent presentation today, Daryl.
You too, Greg.